Since the first humans gathered around flickering flames beneath ancient starlit skies, light has held a sacred place in every culture across our world. The Egyptians built temples aligned to capture the sun's rays on solstices. The Greeks debated whether vision flowed outward from our eyes or inward from luminous objects. Indigenous peoples from every continent wove stories of light bringers and sun gods into the fabric of their understanding. Tonight, we journey together through the complete story of this remarkable phenomenon, from those earliest wanderings to the quantum mysteries that still puzzle physicists today. Let yourself settle into a comfortable position now. Allow your breathing to slow, your muscles to soften, your mind to drift along with these gentle words as we explore everything humanity has discovered about the nature of light itself. Long before the tools of modern science existed, ancient peoples observed light with careful attention and profound reverence. In the warm lands along the Nile River, Egyptian civilization flourished for thousands of years, and at the centre of their spiritual understanding stood Ra, the sun god whose daily journey across the sky represented the eternal cycle of creation, death, and rebirth. Each morning, Ra emerged from the underworld in his solar bark, bringing warmth and visibility to the land of the living. Each evening, he descended again into darkness, battling serpents and chaos through the nighttime hours before rising triumphant once more at dawn. This was not merely mythology to the ancient Egyptians. Their entire society oriented itself around the movements of the sun. Temples at Karnak and Abu Simbel were constructed with extraordinary precision, so that sunlight would penetrate their innermost chambers only on specific days of the year. The Great Pyramids at Giza align with remarkable accuracy to the cardinal directions. Their smooth limestone faces, once gleaming brilliant white in the desert sun, visible for miles as monuments to the connection between earthly power and celestial radiance. The Egyptians understood that all life depended upon the sun's light, that crops grew toward its warmth, that the flooding of the Nile followed predictable patterns tied to the solar calendar. Across the Mediterranean Sea, Greek philosophers approached the mystery of light with questions that still echo through scientific inquiry today. Empedocles, who lived around 490 to 430 BCE, proposed that the goddess Aphrodite had crafted human eyes from the 4 classical elements and placed fire within them. He believed that this inner fire streamed outward from our eyes, mingling with external light to create the experience of vision. This emission theory, as it came to be called, held considerable influence for centuries. It seemed to explain why we cannot see in complete darkness, why our eyes seem to shine within a life, why the act of seeing feels like an active reaching out toward the world rather than a passive reception. Plato, that towering figure of Western philosophy, incorporated similar ideas into his broader understanding of reality. In his dialogue, Timaeus, he described vision as occurring when gentle fire flowing from the eyes meets and coalesces with daylight. This combined stream could then make contact with objects and somehow transmit information about their properties back to the soul. For Plato, the physical world we perceive through our senses was itself merely a shadow of higher, more perfect forms. Light played a crucial role in his famous allegory of the cave, where prisoners chained in darkness mistake flickering shadows for reality until one escapes and gradually accustoms his eyes to the brilliance of the sun, which represents the form of the good, the ultimate source of truth and being. Aristotle, Plato's most famous student, took a different approach. He rejected the emission theory, arguing instead that vision occurred when objects somehow altered the transparent medium between themselves and the eye. For Aristotle, light was not a substance that travelled, but rather a state or quality of the transparent medium. When a luminous body was present, it actualized the potential transparency of air or water, making the medium actually transparent rather than merely potentially so. This might seem strange to modern ears, but Aristotle was grappling with genuine puzzles about the nature of light. He noted that light seemed to appear instantaneously when a lamp was lit, with no apparent travel time across a room. If light were a substance in motion, surely it would take time to cross distances, yet no such delay was observable. Further east in the ancient civilizations of India, light held equally profound significance. The Vedic traditions, stretching back thousands of years before the Common Era, centered much of their spiritual practice around Agni, the god of fire and light. Agni served as the messenger between humans and the divine realm, carrying offerings upward in the smoke of sacred fires. The Rig Veda, among the oldest religious texts still in continuous use, contains numerous hymns praising Agni's brilliance and life-giving power. Light in Vedic thought represented consciousness itself, the inner illumination that allows the soul to perceive truth. The Sanskrit word for light, jyoti, became synonymous with wisdom, awareness, and spiritual enlightenment. The Upanishads, philosophical texts composed somewhat later, developed these ideas further. They spoke of an inner light within every being, identical with the universal light of Brahman, the ultimate reality underlying all existence. To achieve moksha, liberation from the cycle of rebirth, was to recognize this identity between the individual soul and the cosmic light. Meditation practices aimed at perceiving this inner radiance became central to Hindu spiritual discipline. The image of the enlightened sage, whose very presence seems to glow with inner luminosity, reflects this ancient association between light and the highest states of consciousness. In China, philosophical traditions developed their own sophisticated understanding of light and its relationship to the fundamental principles governing the universe. The concept of yang, one half of the famous yin-yang duality, encompassed brightness, warmth, activity, and the masculine principle. Yang energy was associated with the sun, with daytime, with the south-facing slopes of mountains where light fell most directly. The balance and interplay between yin and yang produced all phenomena in the natural world, and light played a crucial role in this cosmic dance. Chinese astronomers carefully tracked the movements of the sun, moon, and stars, developing calendars of remarkable accuracy that guided agricultural activities and religious observances alike. Indigenous cultures across every continent developed their own relationships with light, often encoding sophisticated observational knowledge within mythological frameworks. The Aboriginal peoples of Australia, whose continuous cultures stretch back at least 65,000 years, told stories of the Sun Woman who carried her torch across the sky each day, lighting her fire in the east each morning and carrying its embers westward. Some traditions describe the Milky Way as a river of light connecting the earthly realm to the sky world, where ancestral spirits dwelled. These were not naive imaginings, but rather ways of organizing and transmitting genuine knowledge about celestial patterns, seasonal changes, and the navigation of vast landscapes. In North America, the Hopi people of the American Southwest developed an intricate ceremonial calendar tied to the movements of the sun. Their villages were constructed so that sunlight falling through specific openings would mark the solstices and equinoxes, signaling times for planting, harvesting, and sacred ceremonies. The Lakota people of the Great Plains held the sun dance as their most important religious ceremony, a grueling ritual of sacrifice and renewal that honored the sun's life-giving power. Across the continent, indigenous peoples recognized that light from the sun drove the cycles of nature upon which all life depended. These ancient understandings, whether expressed through mythology, philosophy, or careful observation, shared certain common recognitions. Light made vision possible. Light came primarily from the sun during the day and from fire at night. Light seemed connected to life, warmth, and consciousness. Darkness brought danger, uncertainty, and the unknown. Whatever light actually was, it clearly occupied a special place in the structure of reality, worthy of worship, philosophical investigation, and careful attention. As centuries passed and civilizations rose and fell, the accumulated wisdom of ancient peoples was preserved, translated, and transformed. The great library at Alexandria gathered texts from Greek, Egyptian, Persian, and other traditions, creating a center of learning where different approaches to understanding light could be compared and debated. When that library declined, much of its knowledge dispersed throughout the Mediterranean world, eventually finding new homes in the rising civilization of Islam. The period from roughly the 8th through the 14th centuries saw extraordinary flowering of scientific and philosophical inquiry in the Islamic world. Scholars working in Baghdad, Cairo, Cordoba, and other centers of learning translated Greek texts into Arabic, preserved them, commented upon them, and extended their insights in original ways. Among the most important of these scholars for our story of light was Abu Ali al-Hasan ibn al-Haytham, known in the Latin West as Al-Hazan, who lived from around 965 to 1040 CE. Ibn al-Haytham was born in Basra, in present-day Iraq, and spent much of his working life in Cairo under the patronage of the Fatimid Caliph al-Hakim. He was a polymath who wrote on mathematics, astronomy, medicine, and philosophy, but his most influential work concerned the nature of light and vision. His great treatise, known in Arabic as Kitab al-Manazir and in Latin as De Aspectibus or Perspectiva, systematically demolished the emission theories that had dominated ancient Greek thought and established what we would now call the intromission theory of vision. Ibn al-Haytham argued, with careful reasoning and experimental evidence, that vision occurs when light from external sources enters the eye. He noted that looking at the sun causes pain and can damage the eyes, which would make no sense if vision involved rays emanating outward from the eye. He observed that after looking at a bright light, we continue to see its afterimage even with our eyes closed, suggesting that something from outside had affected the eye's interior. He conducted experiments with the camera obscura, a darkened room with a small hole through which light could enter, showing that light travels in straight lines and that images form by the intersection of these light rays. This might seem obvious to us today, but establishing it required overturning centuries of philosophical authority. Ibn al-Haytham was not merely asserting a different opinion. He was demonstrating through careful observation and logical argument that the ancient theories were wrong. His methodology, combining mathematical reasoning with experimental verification, anticipated the scientific revolution that would transform European thought 6 centuries later. His works were translated into Latin in the 12th and 13th centuries and became foundational texts for European scholars studying optics. Ibn al-Haytham also investigated the behaviour of light in detail. He studied reflection from mirrors, both flat and curved, working out the geometry of how light rays bounce from surfaces. He explored refraction, the bending of light as it passes from one transparent medium to another, such as from air into water or glass. He recognised that refraction explained many optical phenomena, including the apparent bending of a stick partially submerged in water and the focusing of light by curved glass surfaces. Although he did not arrive at the precise mathematical law governing refraction, his careful observations laid groundwork for later discoveries. Beyond his technical contributions, Ibn al-Haytham's approach to knowledge itself proved influential. He emphasized that scientific claims must be tested against observation, that authority alone cannot establish truth, that even the greatest scholars of the past might be wrong. In the introduction to his treatise on optics, he wrote that the seeker after truth is not one who studies the writings of the ancients and puts his trust in them, but rather one who suspects his faith in them and questions what he gathers from them, submitting to argument and demonstration. This spirit of critical inquiry, of testing ideas against evidence, would become central to the scientific method. While Islamic scholars were advancing the study of light, medieval Europe was developing its own relationship with illumination, one deeply intertwined with Christian theology and the architecture of sacred spaces. For medieval Christians, light carried profound spiritual significance. God's first act of creation, according to Genesis, was to speak light into existence, separating it from primordial darkness. Christ described himself as the light of the world. Divine grace was often metaphorically described as illumination, and sin as darkness. This theological framework shaped how medieval Europeans thought about physical light as well. The great Gothic cathedrals constructed between the 12th and 16th centuries embodied this theology in stone and glass. Architects developed new structural techniques, including pointed arches, ribbed vaults, and flying buttresses that allowed walls to be opened up with vast windows. These windows were filled with stained glass depicting biblical scenes, saints' lives, and theological symbols. When sunlight streamed through these coloured panes, it transformed the interior space into something otherworldly, bathing worshippers in blues, reds, and golds that seemed to emanate from heaven itself. The abbot Suger of Saint-Denis, who oversaw the reconstruction of his abbey church in the 1140s, wrote eloquently about the spiritual effects of this architecture. He described how the beauty of the coloured gems in the windows transported his mind from material concerns to immaterial ones, how contemplating the physical light led his soul upward toward the divine light that was its source. This was not mere aesthetic appreciation, but a form of spiritual practice, using the senses as a ladder to transcend the senses. The cathedral became a kind of optical instrument designed to transform ordinary sunlight into a medium of religious experience. Medieval European scholars also engaged with the more technical questions about light that Islamic scholars had investigated. The works of Ibn al-Haytham, along with those of other Arabic authors, were translated into Latin and studied at the new universities emerging in Paris, Oxford, and other cities. Robert Grosseteste, who served as Bishop of Lincoln in 13th century England, wrote extensively on light and optics. He proposed that light was the first form created by God, the basic substance from which all material things were made. Light, for Grosseteste, was not merely one phenomenon among others, but the fundamental principle underlying physical reality. Roger Bacon, a Franciscan friar who studied at Oxford and Paris, took up these ideas and extended them. He conducted experiments with lenses and mirrors, investigating how curved glass surfaces could magnify objects or focus light to a point. He speculated about the possibility of constructing devices that would allow people to see distant objects as if they were near, anticipating the telescope by 3 centuries. Bacon believed that understanding light and optics would yield practical benefits, including improvements in vision for the elderly and new instruments for observation. He also believed that such understanding would illuminate theological truths, since light was God's first creation and bore special relationship to divine nature. These medieval investigations remained limited by the conceptual frameworks available. Scholars still worked within Aristotelian physics, which did not easily accommodate the idea of light as something that travels through space at a finite speed. They lacked precise instruments for measuring optical phenomena and mathematical tools for describing them accurately. But they kept alive the questions that ancient thinkers had raised and added new observations and speculations that would prove valuable when later generations returned to these problems with fresh approaches. The period we call the Renaissance, spanning roughly the 15th through 17th centuries, brought transformed attitudes toward nature, knowledge, and human capability. Artists, architects, engineers, and natural philosophers began systematic investigation of the physical world, combining careful observation with mathematical analysis in ways that would eventually give birth to modern science. Light played a central role in many of these investigations, both as a subject of study in itself and as a tool for understanding other phenomena. Leonardo da Vinci, that extraordinary polymath of the Italian Renaissance, filled his notebooks with observations and speculations about light and shadow. As a painter, he needed to understand how light fell on objects, how shadows formed and gradated, how the atmosphere affected the appearance of distant landscapes. He developed the technique of sfumato, the subtle blending of tones that gives his paintings their characteristic, soft, atmospheric quality. But his interests extended beyond artistic application to theoretical understanding. He conducted experiments with pinhole cameras, observed the behavior of light in water, and speculated about the nature of vision and the anatomy of the eye. Leonardo recognized that light travels in straight lines, that shadows have both fully dark regions and partially illuminated penumbras, that reflected light from surrounding surfaces affects the appearance of objects. He observed that the sky appears blue and speculated about why this might be, noting that distant mountains also take on a bluish tinge. His explanations were not always correct by modern standards, but his careful attention to optical phenomena and his attempts to find underlying principles exemplified the Renaissance approach to nature. Galileo Galilei, working a century after Leonardo, made discoveries about light that would help transform astronomy and physics. In 1609, having heard reports of a Dutch invention that made distant objects appear closer, Galileo constructed his own telescope and turned it toward the heavens. What he saw overturned ancient certainties about the cosmos. The moon's surface was not the perfect, unblemished sphere that Aristotelian philosophy required, but was rough and mountainous, covered with craters and valleys revealed by the play of light and shadow across its face. The Milky Way, that mysterious band of light across the night sky, resolved into countless individual stars, too faint to see with the naked eye. Jupiter was accompanied by 4 moons of its own, orbiting the giant planet, just as our moon orbits Earth. These observations did not directly concern the nature of light itself, but they demonstrated the power of optical instruments to reveal truths hidden from unaided vision. They also raised new questions about light and its behavior. How exactly did the telescope work? What determined how much it magnified? Were there limits to what optical instruments could reveal? Galileo corresponded with Johannes Kepler, the German mathematician and astronomer, about these questions. Kepler had already made important contributions to understanding how light behaves as it passes through lenses and how images form in the eye. Kepler's work on optics, published in 1604 and 1611, represented a significant advance over previous understanding. He correctly described how the eye focuses light onto the retina, with the lens acting to bend rays so that they converge to form an image. He explained nearsightedness and farsightedness in terms of the eye's focusing mechanism and showed how corrective lenses could compensate for these defects. He worked out the mathematics of how lenses of different shapes bend light, laying groundwork for the design of better telescopes and microscopes. He also investigated the behavior of light in the atmosphere, explaining various phenomena, including the apparent flattening of the sun and moon near the horizon. Around the same time, another crucial piece of the puzzle fell into place. Willebrord Snellius, a Dutch mathematician, discovered the precise mathematical law governing refraction. When light passes from one transparent medium into another, such as from air into glass, it bends at the interface between them. Snellius found that the relationship between the angle of the incoming ray and the angle of the refracted ray follows a specific mathematical formula involving the signs of these angles. This law, now known as Snell's law, allowed precise prediction of how light would behave when passing through lenses, prisms, and other optical devices. Snellius did not publish his discovery, and it became widely known only when René Descartes independently derived the same law and included it in his dioptrique of 1637. Descartes was attempting something grander than merely describing how light bends. He wanted to explain why it bends, to provide a mechanical account of light that would fit within his broader philosophy of nature. Descartes envisioned the universe as filled with matter in constant motion, with no empty space anywhere. Light, in his view, was not a substance that travelled through space, but rather a pressure or tendency to motion transmitted instantaneously through the subtle matter filling all of space. This might seem a step backward from Ibn al-Haytham's recognition that light travels from objects to the eye, but Descartes was grappling with a genuine puzzle. If light takes time to travel, then when we look at the sun, we see it not where it actually is, but where it was some time ago. The same would be true of everything we observe. Our visual experience would always lag behind reality. Descartes found this philosophically troubling and preferred to think of light as instantaneous. He was wrong about this, as later measurements would show, but his mechanical philosophy of nature, his insistence on explaining phenomena in terms of matter and motion, proved enormously influential. By the middle of the 17th century, the stage was set for the next great advances in understanding light. Optical instruments were improving rapidly, revealing new wonders in both the heavens and the microscopic world. Mathematical tools for describing the behaviour of light were becoming more sophisticated. Natural philosophers were increasingly committed to explaining phenomena through mechanical causes rather than occult qualities or divine intervention. The questions that ancient thinkers had raised about the nature of light were about to receive answers that would have astonished them. In the year 1666, a young Englishman named Isaac Newton retreated to his family's country estate at Woolsthorpe to escape an outbreak of plague that had closed Cambridge University. He was 23 years old, recently graduated, and already developing the mathematical and physical ideas that would transform science. During this period of rural isolation, Newton conducted experiments with prisms that would reveal the hidden structure of white light and establish him as one of history's greatest investigators of optical phenomena. Newton obtained a glass prism and darkened a room in the farmhouse, allowing only a small beam of sunlight to enter through a hole in the window shutter. When he placed the prism in this beam of light, something wonderful happened. The white sunlight spread out into a band of colours, a spectrum ranging from red at one end through orange, yellow, green, and blue to violet at the other end. This phenomenon was not itself new. People had observed rainbows since ancient times, and the colours produced by prisms had been noted before. But the standard explanation held that the prism somehow modified or corrupted the pure white light, adding colours that were not originally present. Newton suspected otherwise, and he devised a crucial experiment to test his idea. He placed a second prism in the path of the coloured light emerging from the first prism. If the prism were adding colours to the light, then the second prism should add more colours, further modifying the beam. But if, as Newton suspected, the white light already contained all the colours and the prism merely separated them, then the second prism should have a different effect. Newton found that when he selected a single colour from the spectrum, say red light, and passed it through the second prism, it remained red. The prism did not add any new colours to it. Furthermore, when he arranged matters so that all the separated colours passed through the second prism and were recombined, they produced white light again. These experiments demonstrated that white light is not simple, but composite, a mixture of rays of different colours that can be separated and recombined. The prism does not create colours, but reveals colours that were present all along. Newton called this phenomenon the heterogeneous nature of light, and it became a cornerstone of his optical theory. He went further, showing that each colour of light has its own characteristic degree of refrangibility, its own tendency to bend by a specific amount when passing through glass or other transparent materials. Red light bends the least, violet the most, with other colours falling in between. This is why the prism spreads white light into a spectrum. The different colours, having different refrangibilities, separate as they pass through the glass. Newton also investigated what happens when light falls on coloured objects. Why does a red apple appear red? Newton's answer was that the surface of the apple reflects red light while absorbing other colours. The red was already present in the white light illuminating the apple. The apple's surface simply selects which colours to send to our eyes. Similarly, a green leaf reflects green light and absorbs others. When we see colours in the world around us, we are seeing the selective reflection and absorption of the components of white light. These discoveries had practical implications for the design of telescopes. Newton realised that ordinary lenses, which refract light to form images, must suffer from chromatic aberration. Because different colours refract by different amounts, a lens cannot bring all colours to focus at the same point. The image will always be slightly blurred by coloured fringes. To overcome this problem, Newton invented a new type of telescope that used a curved mirror instead of a lens to gather and focus light. Since reflection does not separate colours the way refraction does, the reflecting telescope avoids chromatic aberration. Newton built the first working reflecting telescope in 1668, and the design he pioneered remains in use today in many of the world's largest astronomical instruments. Newton presented his findings on light and colour to the Royal Society in 1672, and they immediately provoked controversy. Robert Hooke, the Society's curator of experiments and a formidable natural philosopher in his own right, criticised Newton's theory. So did Christian Huygens, the brilliant Dutch scientist whose own ideas about light differed fundamentally from Newton's. These disputes would simmer for years and influenced Newton's reluctance to publish his complete optical work until 1704, when his optics finally appeared. Beyond his discoveries about colour, Newton developed a comprehensive theory of what light actually is. He proposed that light consists of tiny particles, which he called corpuscles, emitted by luminous bodies and travelling in straight lines through space. When these corpuscles strike the retina of the eye, they produce the sensation of vision. Different colours correspond to corpuscles of different sizes or other properties. The corpuscular theory explained many optical phenomena in straightforward mechanical terms. Reflection occurs when corpuscles bounce off surfaces. Refraction occurs when corpuscles speed up or slow down as they enter a denser or rarer medium, changing direction in the process. Newton recognised that his corpuscular theory faced some difficulties. One puzzle concerned what happens when light passes from air into glass. According to the corpuscular theory, some light should reflect from the surface, while other light passes through. But what determines which corpuscles reflect and which refract? Newton proposed that corpuscles somehow acquire fits of easy reflection and easy transmission as they travel, periodically alternating between these states. This was an awkward addition to the theory, and Newton himself seemed uncertain about its ultimate explanation. He speculated that the fits might be caused by vibrations in an ethereal medium surrounding the corpuscles, an idea that brought his particle theory closer to the wave theories that his rivals favoured. The optics, when it finally appeared, presented not only Newton's discoveries and theories, but also a series of queries, questions for future investigation. Newton speculated about the relationship between light and other phenomena, including heat, electricity, and the forces that hold matter together. He wondered whether light might be converted into matter and matter into light. He asked whether the rays of light might not be very small bodies emitted from shining substances. These queries revealed that even Newton, for all his achievements, recognized how much remained unknown about the nature of light. Newton's authority dominated 18th century thinking about light, at least in Britain. His corpuscular theory seemed to explain the main optical phenomena, and his experimental discoveries about colour were beyond dispute. But alternative views persisted, particularly on the European continent. The wave theory of light, which Newton had rejected, would eventually mount a successful challenge to the corpuscular view, leading to one of the most dramatic reversals in the history of science. The wave theory of light found its most systematic early advocate in Christian Huygens, a Dutch scientist of remarkable breadth and ability. Huygens had made important contributions to mathematics, astronomy, and mechanics. He invented the pendulum clock, discovered Saturn's moon Titan, and correctly identified the nature of Saturn's rings. His work on light, published in 1690 as Traité de la Lumière, proposed that light consists of waves propagating through an invisible medium that fills all of space. Huygens called this medium the luminiferous ether, borrowing a term from ancient Greek philosophy. He imagined the ether as composed of tiny hard particles packed closely together. When a luminous body vibrates, it disturbs the ether particles nearest to it. These particles then bump into their neighbours, passing the disturbance along. The light we see is not a flow of particles from the source to the eye, but rather a wave of disturbance travelling through the ether, much as a sound wave travels through air without the air itself moving from speaker to listener. This wave picture explains several optical phenomena elegantly. Reflection occurs when waves bounce off surfaces, just as water waves reflect from the edge of a pond. Refraction occurs when waves pass from one medium into another, where they travel at a different speed. Huygens developed a geometrical construction, now called Huygens' principle, that allowed him to predict how wavefronts would propagate and how they would bend upon refraction. His theory correctly predicted that light should travel more slowly in denser media like glass or water than in air, the opposite of what Newton's corpuscular theory required. Despite its successes, Huygens' wave theory had significant weaknesses. Most importantly, it could not explain why light travels in straight lines, casting sharp shadows. Water waves and sound waves bend around obstacles, a phenomenon called diffraction. If light were a wave, why didn't it bend around corners? Huygens was aware of this problem, but could not solve it. His theory also struggled to explain the phenomenon of polarization, which Newton had discovered but not fully understood. When light passes through certain crystals, it splits into two beams with different properties. This seemed difficult to reconcile with simple longitudinal waves like sound. For over a century after Huygens' work, the corpuscular theory held sway, bolstered by Newton's immense prestige. But in the early 19th century, new experiments and theoretical insights would shift the balance decisively toward the wave theory. The key figure in this transformation was Thomas Young, an English polymath whose range of interests and abilities rivaled those of the great natural philosophers of earlier centuries. Young was a physician by profession, but his contributions ranged across physics, physiology, linguistics, and Egyptology. He helped decipher the Rosetta Stone, made important discoveries about the mechanics of the eye, and proposed the three-colour theory of vision that remains fundamental to our understanding of how we perceive colour. But his most famous contribution to physics was his demonstration of the interference of light, which provided compelling evidence for the wave theory. In 1801, Young performed what has become one of the most celebrated experiments in the history of science. He allowed light to pass through two narrow slits in an opaque barrier and observed the pattern that formed on a screen beyond. If light consisted of particles travelling in straight lines, one would expect to see two bright bands on the screen, corresponding to the light passing through each slit. Instead, Young observed a pattern of alternating bright and dark bands, an interference pattern that could only be explained if light behaved as a wave. The explanation is straightforward once one accepts the wave picture. Light waves spreading from each slit overlap and combine on the screen. Where the crests of waves from both slits arrive together, they reinforce each other, producing a bright band. Where a crest from one slit meets a trough from the other, they cancel out, producing a dark band. This interference between waves was well known from studies of water waves and sound. Young's experiment showed that light exhibits the same behaviour, strong evidence that light too is a wave phenomenon. Young's work met resistance, particularly in Britain where Newton's authority remained powerful. Critics questioned his experimental methods and proposed alternative explanations for the interference patterns. But on the continent, especially in France, Young's ideas found more receptive audiences. The French physicist Augustin-Jean Fresnel took up the wave theory and developed it into a comprehensive mathematical framework that could explain virtually all known optical phenomena. Fresnel was a civil engineer by training who turned to physics during a period of political exile from Paris. He combined theoretical brilliance with experimental skill, systematically investigating diffraction, the bending of light around obstacles and through small openings. Where Huygens had struggled to explain why light appears to travel in straight lines despite being a wave, Fresnel provided the mathematical solution. He showed that light waves do indeed bend around obstacles, but because light waves have extremely short wavelengths, the bending is usually too small to notice except under carefully controlled conditions. Fresnel's mathematical treatment of diffraction was remarkably sophisticated. He showed how to calculate the intensity of light at any point by summing the contributions from all parts of a wave front, taking into account how these contributions interfere with one another. His predictions matched experimental observations with impressive precision. When the French Academy of Sciences held a competition in 1818 for the best work on diffraction, Fresnel submitted a memoir that would become a landmark in the history of optics. The judging committee included Siméon Denis Poisson, a supporter of the corpuscular theory, who sought to discredit Fresnel's wave-based approach. Poisson worked through Fresnel's mathematics and discovered what he thought was a fatal flaw. The theory predicted that if light shines on a small circular disk, there should be a bright spot at the very centre of the shadow, behind the disk. This seemed absurd. How could there be light in the middle of a shadow? Poisson presented this prediction as a reductio ad absurdum, proof that the wave theory must be wrong. But when François Arago, another member of the committee, actually performed the experiment, he found the bright spot exactly where Fresnel's theory predicted it would be. What Poisson had intended as a refutation became instead a triumphant confirmation. The spot is now known as the Poisson spot or the Arago spot, a permanent reminder of how experimental evidence can overturn theoretical expectations. Fresnel won the competition, and the wave theory of light gained powerful new support. Fresnel also solved the puzzle of polarization that had troubled earlier wave theorists. He proposed that light waves are not longitudinal, like sound waves, but transverse. In a longitudinal wave, the vibration occurs in the same direction as the wave travels. In a transverse wave, the vibration is perpendicular to the direction of travel. Imagine shaking a rope up and down while the wave travels horizontally along its length. That is a transverse wave. Fresnel showed that if light consists of transverse waves, then polarization becomes easy to understand. Polarized light is simply light in which the transverse vibrations all occur in the same plane rather than in random orientations. This insight had profound implications. It meant that the luminiferous ether, if it existed, must be capable of supporting transverse waves. But transverse waves can only propagate through solids, not through fluids. The ether would have to be an extremely rigid solid filling all of space, yet somehow offering no resistance to the motion of planets and other bodies passing through it. This seemed paradoxical, and the puzzle of the ether's properties would occupy physicists for decades to come. Despite these conceptual difficulties, Fresnel's wave theory proved enormously successful at explaining and predicting optical phenomena. He worked out the laws governing how much light reflects and how much refracts at the boundary between two media, laws that are still used today in designing optical instruments. He invented the Fresnel lens, a thin, lightweight lens made of concentric rings that could focus light as effectively as a much thicker, conventional lens. Fresnel lenses found immediate application in lighthouses, where they dramatically increased the range at which ships could see warning beacons. Many lighthouses around the world still use Fresnel's design today, a practical legacy of his theoretical insights. By the middle of the 19th century, the wave theory of light had achieved near universal acceptance among physicists. Young's interference experiments, Fresnel's mathematical framework, and countless confirming observations had overwhelmed the corpuscular theory. Light was understood to be a wave phenomenon, propagating through the mysterious luminiferous ether that filled all of space. But what kind of wave was it? What exactly was waving? The answers to these questions would come from an unexpected direction, from investigations into electricity and magnetism that seemed at first to have nothing to do with light. The story of how light came to be understood as electromagnetic radiation begins not with optics, but with the curious phenomena of electricity and magnetism. For centuries, these had seemed to be separate forces, related perhaps, but fundamentally distinct. Electricity involved the attraction and repulsion of charged objects, the spark of lightning, the shock from rubbing amber. Magnetism involved the attraction of iron to lodestones, the orientation of compass needles, the invisible influence that seemed to emanate from certain materials. The 19th century would reveal that these phenomena are deeply connected, two aspects of a single electromagnetic force, and that light itself is an electromagnetic phenomenon. The crucial experimental discoveries came in the early decades of the 1800s. In 1820, the Danish physicist Hans Christian Ørsted noticed something remarkable during a lecture demonstration. When he connected a wire to a battery, allowing electric current to flow, a nearby compass needle deflected. This was astonishing. It meant that electric currents produce magnetic effects. Electricity and magnetism were not separate after all, but intimately related. News of Ørsted's discovery spread rapidly through the scientific community, inspiring a flurry of investigations. Within weeks, André-Marie Ampère in France had worked out the mathematical laws governing the magnetic forces between current-carrying wires. He showed that parallel wires carrying current in the same direction attract each other, while wires carrying current in opposite directions repel. Ampère proposed that all magnetism, including that of permanent magnets, arises from electric currents, specifically from tiny circular currents within magnetic materials. This bold hypothesis would eventually prove correct. If electric currents produce magnetic effects, might the reverse also be true? Could magnetism produce electricity? Many scientists attempted to demonstrate this, but success proved elusive. The breakthrough came in 1831, when Michael Faraday in England discovered electromagnetic induction. Faraday found that a changing magnetic field induces an electric current in a nearby conductor. If you move a magnet near a coil of wire, or move the wire near the magnet, or change the strength of the magnetic field in any way, an electric current flows in the wire. This discovery had immense practical consequences. It is the principle behind electric generators, transformers, and much of the electrical technology that powers modern civilization. Faraday was a largely self-educated man who'd risen from humble origins to become one of the greatest experimental scientists in history. He had little mathematical training and expressed his ideas primarily through physical intuition and vivid imagery. One of his most important conceptual contributions was the idea of the field. Rather than thinking of electric and magnetic forces as acting instantaneously across empty space, Faraday imagined space as filled with invisible lines of force. These lines spread out from charged or magnetized objects, filling the surrounding region and mediating the forces between objects. An electric charge does not reach out across space to push or pull another charge. Rather, it creates a field in the space around it, and other charges respond to the field at their own locations. This field concept might seem like a mere visualization tool, a way of picturing forces without changing their mathematical description. But Faraday suspected it was more than that. He believed the field was physically real, that something actually existed in the space between charged and magnetized objects, something that stored energy and transmitted forces. He even speculated that light might be a vibration of these electromagnetic field lines, a wave propagating through the field itself rather than through a separate luminiferous ether. Faraday lacked the mathematical skills to develop these ideas rigorously, but another scientist would take up the challenge. James Clerk Maxwell was a Scottish physicist of extraordinary mathematical ability and physical insight. Born in 1831, the same year Faraday discovered electromagnetic induction, Maxwell would synthesize all known electromagnetic phenomena into a unified mathematical framework, and in doing so, reveal the true nature of light. Maxwell began working on electromagnetism in the 1850s, seeking to translate Faraday's physical intuitions into precise mathematical language. He developed mechanical models of the electromagnetic field, imagining it as a kind of invisible machinery filling space. These models were admittedly artificial, but they helped Maxwell develop the mathematical equations that would prove to be his lasting contribution. By 1865, he had distilled all of electromagnetic theory into a set of equations, originally 20 in number, later reduced by others to the 4 elegant equations that bear his name today. Maxwell's equations describe how electric and magnetic fields are created by charges and currents, and how these fields interact with each other. One equation states that electric field lines diverge from positive charges and converge on negative charges. Another states that magnetic field lines always form closed loops, never beginning or ending on magnetic charges, which do not exist. A third equation expressing Faraday's law of induction states that a changing magnetic field creates an electric field. The fourth equation, incorporating a crucial addition by Maxwell himself, states that a changing electric field creates a magnetic field, just as a changing magnetic field creates an electric field. This last equation was Maxwell's key insight. Ampere's original law described how electric currents create magnetic fields, but Maxwell realized it was incomplete. He added a term representing what he called displacement current, a changing electric field that produces magnetic effects even in the absence of actual moving charges. This addition was necessary for mathematical consistency, but it had profound physical consequences that Maxwell quickly recognized. If a changing magnetic field creates an electric field, and a changing electric field creates a magnetic field, then these fields can sustain each other in a self-propagating wave. Imagine a region of space where the electric field is changing. This changing electric field creates a magnetic field. But now the magnetic field is changing too, which creates an electric field. The fields leapfrog each other through space, each one generating the other, propagating outward as an electromagnetic wave. Maxwell worked out the speed at which such waves would travel. It depended on two constants that had been measured in laboratory experiments on electricity and magnetism, the permittivity and permeability of free space. When Maxwell calculated the wave speed from these constants, he obtained a value remarkably close to the measured speed of light. This could not be a coincidence. Maxwell concluded that light itself is an electromagnetic wave, a self-propagating disturbance in the electric and magnetic fields. This was one of the great unifications in the history of physics. Optics, the study of light, was revealed to be a branch of electromagnetism, the luminiferous ether that physicists had postulated to carry light waves could be identified with the electromagnetic field itself. The entire spectrum of electromagnetic radiation, from the longest radio waves to the shortest gamma rays, was shown to consist of the same fundamental phenomenon, differing only in wavelength and frequency. Maxwell published his electromagnetic theory of light in 1865 in a paper titled A Dynamical Theory of the Electromagnetic Field. He wrote that we can scarcely avoid the inference that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. The transverse nature of light waves, which Fresnel had deduced from polarization experiments, now had a natural explanation. Electromagnetic waves are inherently transverse because the electric and magnetic fields oscillate perpendicular to the direction of wave propagation. Maxwell's theory made predictions that could be tested experimentally. It implied that electromagnetic waves of any frequency should be possible, not just those corresponding to visible light. It predicted that these waves should travel at the same speed regardless of their frequency, and that they should exhibit all the wave properties that light displays, including reflection, refraction, interference, and polarization. Confirming these predictions would require generating and detecting electromagnetic waves in the laboratory, a task that proved challenging but was eventually accomplished. The experimental confirmation came in 1887, 8 years after Maxwell's death, through the work of Heinrich Hertz in Germany. Hertz constructed apparatus that could generate electromagnetic waves by causing electric sparks to jump across a gap between metal electrodes. These sparks created rapidly oscillating currents that radiated electromagnetic waves into the surrounding space. Hertz detected these waves using a simple receiver, a loop of wire with a small gap. When electromagnetic waves struck the receiver, they induced currents that caused tiny sparks to jump across the gap. Hertz demonstrated that his electromagnetic waves behaved exactly as Maxwell's theory predicted. They travelled at the speed of light. They could be reflected from metal surfaces. They could be refracted by prisms made of pitch. They exhibited interference patterns when waves from different sources overlapped. They could be polarized by passing through grids of parallel wires. In every respect they behaved like light, differing only in having much longer wavelengths, in the range we now call radio waves. Hertz's experiments provided decisive confirmation of Maxwell's electromagnetic theory of light. The nature of light, which had puzzled thinkers since antiquity, was finally understood. Light is an electromagnetic wave, a propagating disturbance in electric and magnetic fields that fills all of space. The different colours of visible light correspond to different wavelengths, with red light having longer wavelengths and violet light having shorter wavelengths. Beyond the visible spectrum lie infrared radiation, with wavelengths longer than red, and ultraviolet radiation, with wavelengths shorter than violet. Radio waves, microwaves, X-rays and gamma rays are all electromagnetic radiation, differing from visible light only in wavelength. The electromagnetic spectrum, as it came to be called, spans an enormous range of wavelengths. Radio waves used for broadcasting can have wavelengths of hundreds of meters. Microwaves used in radar and cooking have wavelengths of centimeters. Infrared radiation, which we feel as heat, has wavelengths measured in micrometers. Visible light occupies a narrow band from about 700 nanometers for red to about 400 nanometers for violet. Ultraviolet radiation, X-rays and gamma rays have progressively shorter wavelengths, down to fractions of a nanometer for the most energetic gamma rays. All of these radiations travel at the same speed in vacuum, the speed of light, approximately 299,192 kilometers per second. This speed, usually denoted by the letter c, is one of the fundamental constants of nature. It appears not only in electromagnetic theory, but also, as Einstein would later show, in the basic structure of space and time themselves. Maxwell's unification of light with electricity and magnetism stands as one of the supreme achievements of 19th century physics. It explained a vast range of phenomena within a single theoretical framework. It predicted new phenomena that were subsequently confirmed. It opened the door to technologies that would transform human civilization, from radio communication to television to radar to wireless networks. And yet, even as Maxwell's theory triumphed, new puzzles were emerging that would eventually require a radical revision of how we understand light. The closing years of the 19th century saw physics apparently approaching completion. Newton's mechanics described the motion of objects from falling apples to orbiting planets. Maxwell's electromagnetism explained light, electricity, and magnetism within a unified framework. Thermodynamics governed the behavior of heat and energy. Many physicists believed that the fundamental laws of nature were essentially known, and that future work would consist mainly of refining measurements and working out applications. This confidence would prove spectacularly misplaced. Within a few decades, two revolutionary theories would transform physics: relativity and quantum mechanics. Both would fundamentally alter our understanding of light, and both would emerge in part from puzzles about how light interacts with matter. One of these puzzles concerned the spectrum of light emitted by hot objects. When you heat a piece of metal, it first glows dull red, then bright orange, then yellow, and eventually white hot if it gets hot enough. The colour of the glow depends on the temperature. Physicists in the late 19th century sought to explain this phenomenon using the known laws of thermodynamics and electromagnetism. They imagined an idealized object called a blackbody, a perfect absorber and emitter of radiation, and tried to calculate the spectrum of light it would emit at a given temperature. The calculations led to a disturbing result. According to classical physics, a blackbody should emit infinite amounts of energy at short wavelengths in the ultraviolet and beyond. This was clearly wrong. Hot objects do not emit infinite ultraviolet radiation. The failure of classical physics to explain blackbody radiation became known as the ultraviolet catastrophe, a dramatic name for a problem that pointed to something deeply wrong with existing theories. The solution came from Max Planck, a German physicist who in 1900 proposed a radical hypothesis. Planck suggested that the atoms in a hot object cannot emit or absorb radiation in arbitrary amounts. Instead, energy is exchanged only in discrete packets, which Planck called quanta. The energy of each quantum is proportional to the frequency of the radiation, with the constant of proportionality being a new fundamental constant that we now call Planck's constant, denoted by the letter h. Planck's quantum hypothesis was a mathematical trick that happened to give the right answer for blackbody radiation. Planck himself was uncertain about its physical meaning and hoped that future work would show how it could be reconciled with classical physics. But the quantum idea would prove to be no mere mathematical convenience. It represented a fundamental truth about nature that would reshape all of physics. The physicist who most clearly recognized the revolutionary implications of the quantum was Albert Einstein. In 1905, a year that would become known as his miracle year, Einstein published 4 papers that transformed physics. One of these papers concerned the photoelectric effect, a phenomenon that seemed inexplicable within classical electromagnetic theory. The photoelectric effect occurs when light shines on certain metals and causes them to emit electrons. This had been observed since the late 19th century, but the details of the phenomenon were puzzling. Classical wave theory predicted that brighter light should give the emitted electrons more energy, since brighter light carries more energy. But experiments showed that the energy of the electrons depends not on the brightness of the light, but on its frequency. Blue light ejects faster electrons than red light, regardless of intensity. Furthermore, if the light frequency is too low, no electrons are emitted at all, no matter how bright the light. Einstein explained these observations by proposing that light itself comes in quanta, discrete packets of energy that we now call photons. Each photon carries an energy proportional to its frequency, exactly as Planck had proposed for the energy exchanges between matter and radiation. When light shines on a metal, individual photons are absorbed by individual electrons. If a photon has enough energy, it can knock an electron free from the metal. The energy of the ejected electron depends on the energy of the absorbed photon, which depends on the light's frequency, not its intensity. Brighter light means more photons, which means more electrons are ejected, but each electron has the same energy. Einstein's photon hypothesis was even more radical than Planck's quantum hypothesis. Planck had suggested that matter absorbs and emits radiation in quanta, but he still thought of light itself as a continuous wave. Einstein proposed that light is fundamentally granular, composed of discrete particles of energy. This seemed to contradict a century of evidence that light is a wave, evidence from interference, diffraction, and polarization experiments. How could light be both a wave and a particle? This question, the wave-particle duality of light, would occupy physicists for decades. The answer that eventually emerged is strange and counterintuitive. Light exhibits wave properties in some experiments and particle properties in others. When light passes through a double slit, it creates an interference pattern characteristic of waves. When light ejects electrons from a metal, it behaves as a stream of particles. Both descriptions are correct, but neither is complete. Light is something new, something that does not fit neatly into the classical categories of wave or particle. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921. But his contributions to our understanding of light extended far beyond this single discovery. In the same miraculous year of 1905, Einstein published his special theory of relativity, which placed the speed of light at the very centre of physics. The special theory of relativity grew out of a puzzle that had troubled physicists since Maxwell's time. Maxwell's equations predicted that electromagnetic waves travel at a specific speed, the speed of light. But speed relative to what? In Newtonian physics, speeds are always relative to some frame of reference. A car might be travelling at 60 miles per hour relative to the road, but relative to a passenger inside, it is stationary. What is the speed of light relative to? The natural answer seemed to be that light travels at speed c relative to the luminiferous ether, the medium that carries electromagnetic waves. If you move through the ether, then light travelling in the direction of your motion should appear to move slower relative to you, while light travelling opposite to your motion should appear faster. This is analogous to how the speed of sound changes depending on whether you are moving toward or away from the source, but experiments failed to detect any such effect. The most famous of these was the Michelson-Morley experiment of 1887, which attempted to measure the Earth's motion through the ether by comparing the speed of light in different directions. The experiment found no difference whatsoever. Light appeared to travel at the same speed regardless of the Earth's motion. Einstein resolved this puzzle by taking a bold step. He proposed that the speed of light in vacuum is the same for all observers, regardless of their motion. This is not true of ordinary speeds. If you are on a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone standing by the tracks sees the ball moving at 70 miles per hour. But light does not work this way. If you shine a flashlight from a moving train, both you and the observer by the tracks measure the light travelling at exactly the same speed, approximately 299,792 kilometers per second. This principle, the constancy of the speed of light, has profound consequences. Einstein showed that it requires us to abandon our intuitive notions of absolute space and time. Instead, space and time are intertwined in a four-dimensional continuum called space-time. Observers moving relative to each other disagree about the lengths of objects, the durations of events, and even the simultaneity of events at different locations. These effects are negligible at ordinary speeds, but become significant as speeds approach the speed of light. One consequence of special relativity is that nothing can travel faster than light. As an object speeds up, its energy increases without limit, approaching infinity as its speed approaches c. It would take infinite energy to accelerate any massive object to the speed of light, so this speed represents an absolute cosmic speed limit. Only massless particles, like photons, can travel at exactly the speed of light, and they must always travel at this speed, never faster or slower. Another consequence is Einstein's famous equation E equals mc squared, which reveals that mass and energy are equivalent. A small amount of mass corresponds to an enormous amount of energy, since the speed of light squared is such a large number. This equivalence underlies nuclear reactions, both the destructive power of nuclear weapons and the constructive potential of nuclear power. It also explains how the sun and stars shine, converting mass into energy through nuclear fusion in their cores. The speed of light thus plays a fundamental role in the structure of the universe. It is not merely the speed at which electromagnetic waves happen to travel. It is woven into the fabric of space-time itself, determining the relationships between space and time, between mass and energy. Light is not just something we see, it is a key to understanding the deepest nature of reality. In the years following his 1905 papers, Einstein continued to develop both quantum theory and relativity. In 1916, he published his general theory of relativity, which extended special relativity to include gravity. General relativity describes gravity not as a force but as the curvature of space-time caused by mass and energy. Light follows the curved paths through space-time created by massive objects, an effect that has been confirmed by observations of starlight bending around the sun and by the gravitational lensing of distant galaxies. Einstein also made further contributions to quantum theory, though he grew increasingly uncomfortable with its implications. In 1917, he showed that the quantum theory of light required a new kind of emission process, stimulated emission, in which an incoming photon triggers an atom to emit an identical photon. This process would later become the basis for lasers. But Einstein also highlighted the strange randomness at the heart of quantum mechanics. The fact that we can predict only probabilities, not certainties, for quantum events. He famously objected that God does not play dice with the universe, but the quantum dice playing has been confirmed by countless experiments. The wave-particle duality of light found its fullest expression in the quantum mechanics developed in the 1920s by Werner Heisenberg, Erwin Schrödinger, Max Born, and others. In this framework, light and matter are described by wave functions that encode probabilities rather than definite properties. A photon does not have a definite position until it is measured. Before measurement, it exists in a superposition of all possible positions, with the wave function specifying the probability of finding it at each location. The interference patterns in the double-slit experiment arise because the wave function passes through both slits simultaneously, interfering with itself. This quantum description of light is strange and counterintuitive, but it has been confirmed by experiments with extraordinary precision. It forms the foundation for our modern understanding of how light interacts with matter, how atoms absorb and emit radiation, how lasers work, and how the sun shines. The quantum theory of light, combined with Einstein's relativity, represents our deepest understanding of this phenomenon that has fascinated humanity since the first campfires flickered in the darkness. The development of quantum mechanics in the 1920s provided a powerful framework for understanding atoms, molecules, and the behavior of matter at microscopic scales. But combining quantum mechanics with Einstein's special relativity proved challenging, especially when it came to describing how light interacts with charged particles like electrons. The theory that eventually emerged from this effort, quantum electrodynamics, or QED, represents the most precise and successful theory in all of physics. The first steps toward a relativistic quantum theory of light were taken by Paul Dirac, a British physicist whose mathematical elegance and physical insight placed him among the greatest theorists of the 20th century. In 1927, Dirac developed a quantum theory of the electromagnetic field that treated photons as the quanta of the field, much as Einstein had proposed, but now within a rigorous mathematical framework. Dirac's theory explained how atoms emit and absorb photons, how the intensity of light relates to the number of photons, and how the wave-like and particle-like properties of light emerge from the underlying quantum field. Dirac also developed a relativistic equation for the electron, combining quantum mechanics with special relativity in a way that had profound implications. The Dirac equation predicted the existence of antimatter, particles with the same mass as ordinary particles, but opposite charge. The positron, the antiparticle of the electron, was discovered experimentally in 1932, confirming Dirac's prediction. When an electron and positron meet, they annihilate each other, converting their mass entirely into photons. Conversely, a sufficiently energetic photon can create an electron-positron pair, converting energy into matter. These processes, predicted by Dirac's theory, have been observed countless times in particle physics experiments. Despite these successes, the early quantum theories of light and electrons faced serious difficulties. When physicists tried to calculate certain quantities, like the probability of a photon scattering off an electron, they obtained infinite answers. These infinities appeared because the calculations involved summing contributions from virtual processes at all possible energies, and the sum diverged. The theory seemed to be giving nonsensical results. The resolution of these infinities came in the late 1940s through the work of three physicists working independently: Richard Feynman in the United States, Julian Schwinger, also in the United States, and Shinichiro Tominaga in Japan. Each developed techniques for handling the infinities, extracting finite, physically meaningful predictions from calculations that initially appeared divergent. Their approaches looked very different on the surface, but were shown to be mathematically equivalent. All three shared the Nobel Prize in Physics in 1965 for their contributions to quantum electrodynamics. Feynman's approach has become the most widely used because of its intuitive visual representation. He introduced diagrams, now called Feynman diagrams, that depict the interactions between particles as lines meeting at vertices. An electron is represented by a straight line, a photon by a wavy line. When an electron emits or absorbs a photon, the diagram shows the electron line meeting a photon line at a point. These diagrams are not just pictures, but precise mathematical tools. Each diagram corresponds to a specific mathematical expression, and the probability of a process is calculated by summing the contributions from all possible diagrams. In the quantum electrodynamic picture, the electromagnetic force between charged particles is mediated by the exchange of virtual photons. When two electrons repel each other, they do so by exchanging photons that carry momentum from one electron to the other. These virtual photons are not directly observable. They exist only fleetingly, allowed by the uncertainty principle of quantum mechanics, which permits temporary violations of energy conservation on short enough timescales. The more virtual photons exchanged, the stronger the force. The mathematical machinery of QED allows precise calculation of these exchanges and their effects. The predictions of quantum electrodynamics have been tested with extraordinary precision. One of the most impressive tests involves the magnetic moment of the electron, a measure of how strongly the electron interacts with magnetic fields. QED predicts this quantity to more than 10 decimal places, and experiments have confirmed the prediction to the same precision. The agreement between theory and experiment is better than 1 part in a trillion, making QED the most accurately tested theory in the history of science. Another triumph of QED is its explanation of the Lamb shift, a tiny difference in the energy levels of hydrogen atoms that classical theory could not explain. In 1947, Willis Lamb measured this shift experimentally, and the QED calculations of Feynman, Schwinger, and Tominaga explained it perfectly. The Lamb shift arises from the interaction of the electron with virtual photons that it continuously emits and reabsorbs, a quantum effect with no classical analogue. Quantum electrodynamics also explains phenomena that seem almost magical. Consider the apparent emptiness of the vacuum. Classical physics imagine the vacuum as truly empty, devoid of any matter or energy. But in QED, the vacuum seethes with activity. Virtual particle-antiparticle pairs constantly pop into existence and annihilate, borrowing energy from the vacuum for brief moments allowed by the uncertainty principle. Virtual photons flicker in and out of existence. The vacuum is not empty, but full of quantum fluctuations. These vacuum fluctuations have measurable consequences. The Casimir effect, predicted in 1948 and confirmed experimentally, occurs when two uncharged metal plates are placed very close together. The plates restrict which virtual photons can exist between them, creating an imbalance that pushes the plates together. This tiny force, arising from the quantum nature of the vacuum itself, has been measured and agrees with QED predictions. The success of quantum electrodynamics inspired efforts to develop similar theories for the other fundamental forces of nature. The weak nuclear force responsible for certain types of radioactive decay was unified with electromagnetism in the 1960s and 1970s, creating the electroweak theory. The strong nuclear force, which holds protons and neutrons together in atomic nuclei, is described by quantum chromodynamics, a theory mathematically similar to QED, but involving particles called quarks and gluons, rather than electrons and photons. Together, these theories form the standard model of particle physics, our best current understanding of the fundamental constituents of matter and the forces between them. Light, in this modern understanding, is the quantum field of electromagnetism. Photons are the quanta of this field, the smallest possible excitations of the electromagnetic field. When we see light, we are detecting photons that have travelled from their source to our eyes, interacting with the molecules in our retinas and triggering the neural processes that create visual experience. When radio waves carry music to our receivers, or X-rays reveal the interior of our bodies, or gamma rays stream from distant cosmic explosions, all of these are manifestations of the same quantum electromagnetic field, differing only in the energy and frequency of the photons involved. The journey from ancient wonderings about the nature of light to the precision of quantum electrodynamics spans thousands of years of human inquiry. Each generation built upon the insights of those who came before, asking new questions, devising new experiments, developing new mathematical tools. The story is not finished. Physicists continue to probe the quantum nature of light, exploring phenomena like quantum entanglement, where photons can be correlated in ways that seem to transcend ordinary space and time. New technologies based on the quantum properties of light, including quantum computers and quantum communication systems, are under active development. The story of light continues to unfold. When you look up at the night sky, every point of light you see is a message from the cosmos, a stream of photons that has travelled across the vast emptiness of space to reach your eyes. Some of these photons began their journey mere minutes ago, reflected from the surface of the moon. Others left their sources years, centuries, or even billions of years in the past, carrying information about stars, galaxies, and cosmic events across unimaginable distances. Light is our primary messenger from the universe, and learning to read its messages has revealed the true scale and nature of the cosmos. The Sun, our nearest star, provides the most immediate example of stellar light. Every second, the Sun pours out energy equivalent to billions of nuclear bombs, radiating in all directions as electromagnetic waves. This energy originates in the Sun's core, where temperatures reach about 15 million degrees Celsius, and pressures are so extreme that hydrogen nuclei are forced together, fusing into helium and releasing energy in the process. This nuclear fusion is the source of virtually all the light and heat that makes life on Earth possible. The photons produced in the Sun's core do not travel directly to the surface. The Sun's interior is so dense that photons are constantly absorbed and re-emitted by the surrounding matter, following a random zigzag path that takes, on average, about 170,000 years to traverse the roughly 700,000 kilometers from core to surface. When photons finally reach the Sun's visible surface, the photosphere, they stream outward into space, reaching Earth in just 8 minutes and 20 seconds. The sunlight warming your face began its journey in the Sun's core before modern humans existed, yet crossed the final gap from Sun to Earth in less time than it takes to boil an egg. The light from the Sun is not uniform, but contains a wealth of information encoded in its spectrum. When sunlight is spread out by a prism or diffraction grating, it reveals not only the familiar rainbow of colours, but also hundreds of dark lines crossing the spectrum. These absorption lines, first systematically studied by Joseph von Fraunhofer in the early 19th century, occur because atoms in the Sun's outer atmosphere absorb light at specific wavelengths corresponding to the energy differences between their electron orbitals. Each chemical element produces a unique pattern of absorption lines, a spectral fingerprint that allows astronomers to determine the composition of the sun and stars without ever visiting them. Helium, the second most abundant element in the universe, was discovered in the sun's spectrum before it was found on Earth. Its name derived from Helios, the Greek god of the sun. Spectroscopy has revealed that the sun is composed primarily of hydrogen and helium, with smaller amounts of heavier elements like oxygen, carbon, and iron. The same spectroscopic techniques applied to other stars have shown that they too are balls of hot gas, shining by nuclear fusion in their cores. Stars come in a tremendous range of sizes, temperatures, and luminosities. Red dwarf stars, the most common type in the galaxy, are small and cool, glowing with a dim reddish light. Blue giant stars are massive and hot, blazing with intense blue-white brilliance that outshines our sun by tens of thousands of times. Between these extremes lie yellow stars like our sun, orange stars slightly cooler, and white stars somewhat hotter. The colour of a star directly reveals its surface temperature, a relationship that astronomers use to classify and understand stellar populations throughout the cosmos. The temperature of a star's surface determines not only its colour, but also the peak wavelength of its emission. This relationship, known as Wien's displacement law, tells us that hotter objects emit light at shorter wavelengths. A star with a surface temperature of about 3,000 degrees Celsius glows predominantly in red and infrared light. Our Sun, with a surface temperature of about 5,500 degrees Celsius, emits most strongly in the yellow-green part of the spectrum, though our eyes perceive it as white because it emits across the entire visible range. A star at 10,000 degrees appears blue-white, with much of its energy radiated in the blue and ultraviolet portions of the spectrum. This connection between temperature and light allows astronomers to measure the temperatures of stars billions of light years away simply by analysing the light that reaches our telescopes. The same principle applies to any hot object. The glowing coils of an electric heater, the molten metal in a foundry, the filaments of an incandescent bulb, all emit light whose colour and spectrum reveal their temperatures. The universe speaks to us through the language of light, and learning this language has opened windows onto cosmic processes we could never directly observe. Beyond revealing composition and temperature, starlight carries information about motion. When a star moves toward us, the light waves it emits are compressed, shifting towards shorter wavelengths and bluer colours. When a star moves away, the waves are stretched, shifting toward longer wavelengths and redder colours. This Doppler effect, named after the Austrian physicist Christian Doppler, who first described it for sound waves in 1842, allows astronomers to measure the velocities of stars and galaxies along our line of sight. The Doppler shift of starlight led to one of the most profound discoveries in the history of science. In the 1910s and 1920s, astronomers began systematically measuring the spectra of distant galaxies, those fuzzy patches of light that telescopes revealed to be vast collections of stars far beyond our own Milky Way. Vesto Slipher, working at Lowell Observatory in Arizona, found that most galaxies showed red-shifted spectra, indicating they were moving away from us. Edwin Hubble, using the powerful new 100-inch telescope at Mount Wilson in California, combined these velocity measurements with distance estimates to make a startling discovery. Hubble found that distant galaxies are receding from us, and the farther away a galaxy is, the faster it recedes. This relationship, now known as Hubble's law, implies that the universe is expanding. Space itself is stretching, carrying galaxies apart like raisins in a rising loaf of bread. The light from distant galaxies is redshifted, not because the galaxies are moving through space, but because space itself has expanded during the time the light was travelling, stretching the wavelength of the light along with it. This cosmic expansion has profound implications. If the universe is expanding now, it must have been smaller in the past. Tracing this expansion backward in time leads to the conclusion that the universe began in an extremely hot, dense state approximately 13.8 billion years ago, an event we call the Big Bang. The light from distant galaxies is not merely telling us about those galaxies, it is revealing the history and evolution of the cosmos itself. The most ancient light we can observe is the cosmic microwave background radiation, a faint glow that fills all of space and carries information from the earliest epoch of cosmic history. This radiation originated about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this recombination, the universe was filled with a hot plasma that scattered light, making it opaque. When neutral atoms formed, light could suddenly travel freely through space, and the universe became transparent. The light released at this moment has been travelling through space ever since, stretching as the universe expanded. What began as brilliant visible light has been redshifted by a factor of about 1 × 100, transforming into microwave radiation with a temperature of just 2.7 degrees above absolute zero. This cosmic microwave background was first detected in 1965 by Arno Penzias and Robert Wilson, who initially thought the faint microwave hiss in their antenna was caused by pigeon droppings. Their discovery provided powerful confirmation of the Big Bang theory and earned them the Nobel Prize in Physics. Detailed observations of the cosmic microwave background have revealed tiny fluctuations in its temperature, variations of only a few hundred thousandths of a degree from one part of the sky to another. These fluctuations are the seeds from which all cosmic structure grew. Regions that were slightly denser than average in the early universe had slightly stronger gravity, attracting more matter over time and eventually forming the galaxies, galaxy clusters, and cosmic web of filaments we observe today. The pattern of fluctuations in the microwave background encodes information about the composition, geometry, and age of the universe, allowing cosmologists to measure these fundamental parameters with remarkable precision. Light from the cosmic microwave background has been travelling for nearly the entire history of the universe, about 13.8 billion years. But we can also observe light from objects almost as old. The most distant galaxies detected by modern telescopes emitted their light when the universe was less than 1 billion years old. This light has been travelling toward us for over 13 billion years, showing us galaxies as they appeared in the cosmic dawn, when the first stars and galaxies were forming from primordial gas. The James Webb Space Telescope, launched in December 2021, was specifically designed to observe this ancient light. Its large mirror and infrared sensitivity allow it to detect the highly redshifted light from the earliest galaxies, light that has been stretched by cosmic expansion from visible wavelengths into the infrared. Early observations from Webb have revealed galaxies forming earlier than expected, challenging our models of cosmic evolution and demonstrating that the universe still holds surprises for those who know how to read its light. Light also carries information about some of the most violent events in the cosmos. When massive stars exhaust their nuclear fuel, they can collapse and explode as supernova, briefly outshining entire galaxies. The light from these explosions tells us about the physics of stellar death and the synthesis of heavy elements. Many of the atoms in your body, including the calcium in your bones and the iron in your blood, were forged in the cores of massive stars and scattered into space by supernova explosions billions of years ago. You are, quite literally, made of stardust, and it is light that has revealed this cosmic genealogy. A particular type of supernova, called Type 1a, has proven especially valuable for cosmology. These explosions occur in binary star systems and reach a consistent peak brightness, making them useful as standard candles for measuring cosmic distances. By comparing the apparent brightness of Type 1a supernova in distant galaxies with their known intrinsic brightness, astronomers can determine how far away those galaxies are. In the late 1990s, observations of distant Type 1a supernovae led to another revolutionary discovery. The expansion of the universe is accelerating. This acceleration was completely unexpected. Gravity should be slowing the expansion down, as the mutual attraction of all the matter in the universe acts as a cosmic brake. Instead, something is pushing the universe apart with ever-increasing speed. Cosmologists call this mysterious influence dark energy, though the name reveals our ignorance more than our understanding. Dark energy appears to make up about 68% of the total energy content of the universe, yet we have no idea what it actually is. The light from distant supernovae has revealed that the universe is dominated by something we cannot see or explain, one of the greatest mysteries in modern physics. Closer to home, light carries information about the planets, moons, asteroids, and comets of our own solar system. When sunlight reflects from the surface of Mars, it carries the spectral signature of iron oxide minerals that give the planet its reddish colour. Light reflected from the icy moons of Jupiter and Saturn reveals water ice, ammonia ice, and organic compounds on their surfaces. The atmospheres of planets absorb and emit light at characteristic wavelengths, allowing astronomers to determine their composition without sending spacecraft to visit them. This technique of remote sensing through light has been extended to planets orbiting other stars, worlds so distant that they appear as mere points of light, even in our most powerful telescopes. When an exoplanet passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. By analysing how the spectrum of this light changes during the transit, astronomers can identify molecules in the exoplanet's atmosphere. Water vapour, carbon dioxide, methane, and other compounds have been detected in the atmospheres of distant worlds, raising tantalising questions about the possibility of life beyond Earth. The search for extraterrestrial life is fundamentally a search for signatures in light. If life exists on other worlds, it might reveal itself through biosignatures, chemical compounds in planetary atmospheres that are produced by living organisms. On Earth, the presence of oxygen and methane together is a biosignature, because these gases react with each other and would disappear without biological processes to replenish them. Future telescopes may be able to detect similar biosignatures in the atmospheres of Earth-like planets orbiting nearby stars, potentially answering one of humanity's oldest questions: are we alone in the universe? Light also enables our search for intelligent life beyond Earth. Radio waves, a form of electromagnetic radiation, just like visible light, but with much longer wavelengths, travel easily through the interstellar medium and can be detected across vast distances. Since the 1960s, the search for extraterrestrial intelligence, or SETI, has listened for radio signals that might indicate the presence of technological civilizations elsewhere in the galaxy. No confirmed detection has been made, but the search continues, scanning the skies for a message carried on waves of light. Our own civilization has been broadcasting its presence into space for over a century. Radio and television signals leak outward from Earth at the speed of light, forming an expanding bubble of electromagnetic radiation that now extends more than 100 light-years into space. Any civilization with sufficiently sensitive receivers within that bubble could potentially detect our presence. We have also sent intentional messages towards specific star systems, encoding information in radio waves in the hope that someone might be listening. Light is our messenger to the cosmos, just as it brings messages from the cosmos to us. The study of cosmic light has transformed our understanding of the universe. We have learned that we live on a small planet, orbiting an ordinary star in the outskirts of a galaxy, containing hundreds of billions of stars. Our galaxy is one of hundreds of billions of galaxies in the observable universe, each containing billions of stars, many with planets of their own. The universe is 13.8 billion years old, began in a hot, dense state, and has been expanding ever since. It is dominated by mysterious dark matter and dark energy that we do not understand. All of this knowledge has come from analysing the light that reaches our telescopes, reading the messages that the cosmos sends across the void. As you lie here in the quiet darkness, consider that photons are streaming through space all around you. Some were emitted by the sun 8 minutes ago. Some left distant stars centuries ago. Some have been travelling since the cosmic dawn, carrying information from the earliest epochs of cosmic history. Light connects us to the universe, making visible the invisible, revealing the distant and the ancient, telling stories written in wavelengths and frequencies. Every beam of light is a thread in the vast web of cosmic connection, linking us to stars and galaxies across billions of light years of space and billions of years of time. The story of light is not only a tale of scientific discovery, but also a history of human ingenuity, of our efforts to create, control, and harness light for our own purposes. From the first controlled fires kindled by our distant ancestors to the sophisticated photonic technologies of today, the manipulation of light has been central to human civilization. Each advance in lighting technology has transformed how we live, work, and understand the world around us. The control of fire was perhaps the most significant technological achievement in human prehistory. Archaeological evidence suggests that our ancestors began using fire at least 1 million years ago, though controlled fire making may have developed more recently. Fire provided warmth, protection from predators, and the ability to cook food, which may have contributed to the evolution of our large, energy-hungry brains. But fire also provided light, extending the usable hours of the day and pushing back the darkness that had confined human activity since the beginning of life on Earth. Imagine the profound impact of that first controlled flame. For millions of years, our ancestors had been creatures of the day, retreating to safety when the sun set and predators emerged. Fire changed everything. A campfire created a circle of light in the darkness, a space where humans could gather, eat, talk, and work even after sunset. The flickering flames may have inspired the first storytelling, the first art, the first religious rituals. Fire was not just a tool, but a transformative technology that reshaped human society and culture. For most of human history, fire in various forms remained the primary source of artificial light. Torches, made by wrapping combustible materials around sticks, provided portable illumination. Oil lamps, burning animal fat or plant oils in shallow dishes with fibre wicks, offered steadier light for indoor use. Candles, developed independently in several ancient civilizations, provided convenient, portable light sources that could be made from beeswax, tallow, or other waxy substances. These technologies improved gradually over millennia, but the basic principle remained the same: burning fuel to produce light. The limitations of fire-based lighting shaped human life in ways we can scarcely imagine today. Artificial light was expensive, so most people went to bed when the sun set and rose when it rose. Indoor spaces were dim and smoky, with oil lamps and candles providing barely enough light to work by. Reading and writing after dark were luxuries available mainly to the wealthy. The night belonged to darkness, crime and fear. Cities employed watchmen to patrol the streets and call out the hours, providing some measure of security in the absence of adequate lighting. The 19th century brought revolutionary changes in lighting technology. Gas lighting, using coal gas, piped through networks of underground pipes to street lamps and indoor fixtures, transformed urban life. London became the first city to install gas streetlights on a large scale, beginning in 1812. The new lights were brighter and more reliable than oil lamps, and they could be turned on and off from a central location. Gaslit streets were safer and more inviting, encouraging people to venture out after dark. Theatres, shops, and restaurants could stay open into the evening, creating new patterns of urban entertainment and commerce. Gaslighting reached its peak in the late 19th century, but it was already being challenged by an even more revolutionary technology: electric light. The development of practical electric lighting involved contributions from many inventors and scientists, but the names most associated with it are Thomas Edison in America and Joseph Swan in England, who independently developed commercially viable incandescent light bulbs in the late 1870s. The incandescent bulb works by passing electric current through a thin filament, heating it until it glows white hot. The challenge was finding a filament material that would glow brightly without quickly burning out. Edison tested thousands of materials before settling on carbonized bamboo, which could last over 1,200 hours. Later improvements substituted tungsten filaments, which could be heated to higher temperatures for brighter light and longer life. The tungsten incandescent bulb became the standard light source for most of the 20th century. Electric light transformed society even more profoundly than gas lighting had. Unlike gas, electricity could be transmitted over long distances and distributed safely within buildings. Electric lights produced no smoke or fumes, making indoor air cleaner and healthier. They could be switched on instantly, without the delay of lighting a flame. They were safer, eliminating the fire hazards associated with open flames. And they could be made in a wide range of sizes and shapes, suitable for everything from tiny indicator lights to powerful searchlights. The spread of electric lighting reshaped the patterns of daily life. Factories could operate around the clock, increasing productivity, but also creating new demands on workers. Cities became brighter and more vibrant at night, with illuminated signs, shop windows, and entertainment venues. The distinction between day and night, which had governed human activity since the dawn of our species, began to blur. We became creatures of artificial light, able to work, play, and socialize at any hour. The 20th century brought continued innovations in lighting technology. Fluorescent lamps, developed in the 1930s, produced light more efficiently than incandescent bulbs by exciting a phosphor coating with ultraviolet radiation from an electric discharge through mercury vapor. Fluorescent lights became standard in offices, schools, and commercial buildings, providing bright, even illumination at lower energy costs than incandescent bulbs. High-intensity discharge lamps, including mercury vapor, metal halide, and sodium vapor types, provided powerful illumination for streetlights, stadiums, and industrial applications. The most recent revolution in lighting has come from light-emitting diodes, or LEDs. These semiconductor devices produce light when electric current passes through them, exciting electrons that release photons as they return to lower energy states. LEDs were first developed in the 1960s, but initially produced only dim red light suitable for indicator displays. Decades of research gradually extended their capabilities to other colours and higher brightness levels. The development of efficient blue LEDs in the 1990s, which earned Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura the Nobel Prize in Physics in 2014, opened the door to white LED lighting by combining blue LEDs with phosphor coatings. LED lighting has transformed the economics and environmental impact of illumination. LEDs convert electricity to light far more efficiently than incandescent bulbs, which waste most of their energy as heat. A modern LED bulb can produce the same amount of light as a 60-watt incandescent bulb, while using only about 8 watts of electricity. LEDs also last much longer, typically 25,000 hours or more compared to about 1,000 hours for incandescent bulbs. The widespread adoption of LED lighting is significantly reducing global energy consumption and carbon emissions associated with illumination. Beyond general illumination, light has become a tool for an astonishing range of technologies. The laser, whose name stands for light amplification by a stimulated emission of radiation, produces light with properties unlike any natural source. Laser light is coherent, meaning all the waves are in phase with each other, travelling in lockstep like soldiers marching in formation. It is also monochromatic, consisting of a single precise wavelength and highly directional, spreading very little, even over long distances. The theoretical foundation for lasers came from Einstein's 1917 work on stimulated emission, but practical laser devices were not developed until 1960, when Theodore Myman built the first working laser using a synthetic ruby crystal. Since then, lasers have found applications in virtually every field of technology and science. Laser pointers and barcode scanners use low-power lasers for everyday tasks. Laser printers and optical disc players rely on precisely focused laser beams to read and write information. Industrial lasers cut and weld metal with precision impossible for mechanical tools. Medical lasers perform delicate surgeries, correcting vision, removing tumours, and treating skin conditions. Lasers have also enabled revolutionary scientific instruments. Laser interferometers can measure distances with precision better than the diameter of an atom. The LIGO observatories, which detected gravitational waves for the first time in 2015, use laser interferometry to measure the tiny distortions in space caused by colliding black holes billions of light years away. Laser cooling techniques, which use carefully tuned laser beams to slow atoms almost to a standstill, have enabled the creation of exotic states of matter and ultra-precise atomic clocks. Laser spectroscopy allows scientists to probe the structure of atoms and molecules with unprecedented detail. Fiber optics represents another transformative application of light technology. Optical fibers are thin strands of glass or plastic that guide light through total internal reflection, trapping the light inside the fiber as it bounces along its length. Information encoded in pulses of laser light can travel through optical fibers with very little loss, allowing data to be transmitted over long distances at enormous rates. The global telecommunications network now relies primarily on fiber optic cables for long-distance transmission. Undersea cables carrying laser light connect continents, enabling the instantaneous global communication we take for granted. A single optical fiber can carry trillions of bits of information per second, enough for millions of simultaneous phone calls or video streams. The Internet, with all its transformative effects on society, depends fundamentally on our ability to encode information in light and send it racing through glass fibers at nearly the speed of light. Light is also central to the emerging field of quantum technology. Photons, the quantum particles of light, have properties that make them ideal for quantum information processing. They can exist in superpositions of states, be entangled with other photons across vast distances, and travel through optical fibers or free space without significant decoherence. Quantum cryptography systems use the quantum properties of photons to enable communication that is theoretically immune to eavesdropping. Any attempt to intercept the photons disturbs their quantum states in detectable ways, alerting the communicating parties to the intrusion. Quantum computers, which promise to solve certain problems far faster than any classical computer, may ultimately rely on photonic technologies. Several approaches to quantum computing use photons as the carriers of quantum information, manipulating them with optical elements to perform quantum logic operations. While practical quantum computers remain a work in progress, the field is advancing rapidly, and light-based approaches are among the most promising. The manipulation of light at the smallest scales has given rise to the field of nanophotonics. By structuring materials at scales comparable to the wavelength of light, scientists can create devices with remarkable optical properties. Photonic crystals are materials with periodic structures that affect how light propagates through them, creating forbidden frequency bands where light cannot travel. Metamaterials are engineered structures that can bend light in unusual ways, potentially enabling invisibility cloaks and superlenses that overcome the normal limits of optical resolution. Plasmonics exploits the interaction between light and the free electrons in metals, concentrating electromagnetic energy into spaces far smaller than the wavelength of light. This enables nanoscale optical devices and sensors with extraordinary sensitivity. A single molecule can be detected by its effects on plasmonic resonances, opening new possibilities for medical diagnostics, environmental monitoring, and fundamental research. Solar cells convert light directly into electricity, harnessing the energy that streams from the sun to power our civilization. The photovoltaic effect, discovered in the 19th century, occurs when photons strike certain materials and knock electrons free, creating an electric current. Modern solar cells, typically made from silicon or other semiconductors, can convert more than 20% of incident sunlight into electricity. As manufacturing costs have plummeted and efficiencies have improved, solar power has become one of the cheapest sources of new electricity generation in many parts of the world. The transition to solar energy represents a return to our most ancient energy source. For billions of years, life on Earth has been powered by sunlight, captured by photosynthetic organisms and passed up the food chain. Fossil fuels are themselves stored sunlight, the energy of ancient photosynthesis preserved in coal, oil, and natural gas. By harvesting sunlight directly with solar cells, we tap into the same energy source that has sustained life since its beginning, but without the pollution and climate disruption caused by burning fossil fuels. Light-based technologies continue to advance at a remarkable pace. Optogenetics uses light to control the activity of genetically modified neurons, allowing neuroscientists to study brain circuits with unprecedented precision. Photodynamic therapy uses light-activated drugs to destroy cancer cells while sparing healthy tissue. LiDAR systems use laser pulses to map environments in 3 dimensions, enabling autonomous vehicles to navigate safely. Optical tweezers use focused laser beams to trap and manipulate microscopic objects, including individual cells and molecules. From the first campfires to quantum photonics, the human relationship with light has been one of continual discovery and innovation. Each advance has opened new possibilities, transforming how we see the world and how we live in it. The technologies of light have extended our days, connected our world, healed our bodies, and expanded our knowledge. And the story is far from over. As we develop new ways to create, control, and understand light, we continue a journey that began when our ancestors first gazed in wonder at the flames dancing in the darkness. As we near the end of our journey through the story of light, let us pause to reflect on what this remarkable phenomenon has taught us about the nature of reality itself. Light has been more than just a subject of scientific investigation. It has been a guide leading us toward deeper understanding of the universe and our place within it. The questions that light has raised and the answers it has revealed touch on the most fundamental aspects of existence. Consider what light has shown us about the nature of space and time. Einstein's special theory of relativity, built on the constancy of the speed of light, revealed that space and time are not the absolute, unchanging backdrop that Newton imagined. They are flexible, relative, intertwined. What one observer measures as a certain length or duration, another observer moving at a different speed may measure differently. The only thing that remains constant for all observers is the speed of light itself, that cosmic speed limit woven into the fabric of reality. This discovery has profound philosophical implications. It tells us that our intuitive notions of space and time, developed through everyday experience with objects moving at ordinary speeds, do not accurately describe the deep structure of the universe. Reality is stranger than common sense suggests. The universe operates according to principles that can be grasped through mathematics and careful experiment, but that defy our evolved intuitions. Light has been our teacher, showing us that nature is under no obligation to conform to our expectations. The quantum nature of light raises even more challenging questions. In the quantum world, light exists as both wave and particle, depending on how we choose to observe it. A photon passing through two slits seems to go through both simultaneously, interfering with itself to create patterns that only waves can produce. Yet when we detect the photon, it always appears at a single location, as a particle must. The act of observation seems to determine which aspect of light's nature manifests. This wave-particle duality is not a peculiarity of light alone. Quantum mechanics has revealed that all matter exhibits the same dual nature. Electrons, atoms, even large molecules show interference patterns when passed through appropriate apparatus. The distinction between waves and particles, so clear in everyday experience, dissolves at the quantum level. Light led us to this discovery, but the lesson applies to all of physical reality. The interpretation of quantum mechanics remains a subject of debate among physicists and philosophers. Some argue that the wave function, which describes the quantum state of a system, represents physical reality itself, a kind of smeared-out existence that collapses into definite form only upon measurement. Others maintain that the wave function is merely a mathematical tool for calculating probabilities, not a description of what actually exists. Still others propose that every possible outcome of a quantum measurement actually occurs in separate branches of an ever-splitting multiverse. Light, in its quantum strangeness, has forced us to confront questions about the nature of reality that philosophers have debated for millennia. Quantum entanglement, a phenomenon that Einstein famously called spooky action at a distance, presents perhaps the deepest puzzle. When two photons are entangled, measuring the state of one instantly determines the state of the other, no matter how far apart they are. This correlation is not due to any signal passing between the photons, which would have to travel faster than light. Rather, the two photons seem to share a single quantum state that encompasses both of them, regardless of their separation in space. Experiments have confirmed that entanglement is real and that no local hidden variables can explain the correlations. The universe is, in some sense, more interconnected than classical physics imagined. Distant events can be correlated in ways that cannot be explained by any influence travelling through space, at or below the speed of light. What this means for our understanding of reality remains unclear, but light has once again led us to the frontier of knowledge, showing us that the universe holds mysteries we have barely begun to fathom. Light has also shaped our understanding of the cosmos and our place within it. Before we learn to read the messages carried by starlight, humans imagined themselves at the centre of a small, Earth-centred universe. The sun, moon and stars were thought to revolve around us, placed in the heavens for our benefit. Light from distant objects has revealed a very different picture. We live on a small planet orbiting an ordinary star in the outskirts of a galaxy containing hundreds of billions of stars. Our galaxy is one of hundreds of billions in the observable universe. The cosmos is unimaginably vast, ancient, and indifferent to human concerns. This cosmic perspective can be humbling, even unsettling. We are not the centre of creation, but inhabitants of a tiny speck in an immense universe. Yet there is also something ennobling in this view. We are the universe becoming conscious of itself, matter organised in such a way that it can contemplate its own existence. The atoms in our bodies were forged in the cores of stars, scattered by supernova explosions, gathered into planets, and assembled by billions of years of evolution into beings capable of understanding their own cosmic origins. Light has revealed this story to us, connecting us to the stars from which we came. Looking to the future, light will continue to play a central role in our quest to understand the universe. New telescopes, both on the ground and in space, will gather light from ever more distant objects, probing the earliest epochs of cosmic history. The James Webb Space Telescope is already revealing galaxies from the cosmic dawn, and future instruments will push even further. We may eventually detect light from the first stars that ever formed, witnessing the moment when the universe emerged from the cosmic dark ages. Gravitational wave observatories, while not detecting light directly, work in concert with electromagnetic telescopes to study cosmic events. When two neutron stars collided in 2017, both gravitational waves and light from the event were detected, inaugurating the era of multi-messenger astronomy. Future observations will combine gravitational waves, electromagnetic radiation across the spectrum, and perhaps neutrinos and cosmic rays to build comprehensive pictures of the most violent events in the universe. The search for life beyond Earth will rely heavily on light. Future space telescopes may be able to analyze the atmospheres of Earth-like exoplanets, searching for biosignatures that would indicate the presence of life. The detection of oxygen, methane, or other biological indicators in the atmosphere of a distant world would be one of the most profound discoveries in human history. Light would carry this momentous news across the light years, just as it has carried so many other cosmic messages. Close to home, light-based technologies will continue to transform human society. Quantum computers based on photonic systems may eventually solve problems beyond the reach of any classical computer, revolutionizing fields from drug discovery to cryptography to artificial intelligence. Quantum communication networks will enable perfectly secure transmission of information, with any eavesdropping attempt immediately detectable. These technologies will rely on our deep understanding of the quantum nature of light, turning abstract physics into practical tools. Solar energy will play an increasingly important role in powering human civilization. As climate change accelerates and fossil fuel reserves dwindle, the transition to renewable energy becomes ever more urgent. Sunlight delivers more energy to Earth in 1 hour than humanity uses in an entire year. Harnessing even a small fraction of this bounty through solar cells and other technologies could provide abundant clean energy for all of humanity. Light from our nearest star may prove to be the key to a sustainable future. Medical applications of light will continue to advance. Optical imaging techniques allow doctors to see inside the body without surgery, detecting diseases at earlier, more treatable stages. Laser surgeries correct vision, remove tumours, and repair tissues with precision impossible for mechanical instruments. Photodynamic therapies use light-activated drugs to destroy cancer cells while sparing healthy tissue. Optogenetics allows researchers to control brain activity with light, opening new approaches to treating neurological disorders. Light has become a tool for healing as well as understanding. The story of light is ultimately a story of human curiosity and ingenuity. From the first wanderings of ancient philosophers to the sophisticated theories of modern physics, from the first controlled fires to the latest quantum technologies, we have sought to understand and harness this fundamental phenomenon. Each generation has built upon the insights of those who came before, asking new questions, devising new experiments, developing new technologies. The story is not finished. It continues in laboratories and observatories around the world, wherever curious minds probe the mysteries of light. As you lie here in the peaceful darkness, perhaps you can sense the light that surrounds you even now. Infrared radiation from warm objects nearby, radio waves passing through the walls, carrying signals from distant transmitters. The faint cosmic microwave background, remnant of the Big Bang itself, pervading all of space. Light in all its forms fills the universe, connecting everything to everything else, carrying energy and information across the void. And when morning comes, sunlight will stream through your window, photons that left the sun 8 minutes earlier, themselves the product of nuclear fusion reactions in the solar core. That light will strike your retinas, triggering cascades of neural activity that create the experience of seeing. You will perceive colours, shapes, and movements, constructing from patterns of light a rich visual world. This everyday miracle, so familiar that we rarely pause to consider it, is the culmination of billions of years of evolution and thousands of years of human inquiry. Light has been our constant companion throughout history, illuminating our world, inspiring our art, driving our science, powering our technology. It has revealed the structure of atoms and the expansion of the universe. It has shown us our cosmic origins and our place in the vast web of existence. It has raised questions we are still struggling to answer and pointed toward mysteries we have barely begun to explore. So as you drift towards sleep, carry with you the wonder of light. Remember that every photon has a story, every beam of light a message from across space and time. The universe speaks to us through light, and we have learned slowly and painstakingly to listen. May that gentle illumination accompany you into dreams, and may you wake refreshed, ready to see the world anew in the light of another day. Thank you so much for joining me on this journey through the entire story of light. I hope you found it as fascinating as I do. If you enjoyed this exploration, please consider giving this video a like and subscribing to the channel. Your support helps me create more content like this, diving deep into the wonders of our universe. Hit that notification bell so you never miss a new video. Sweet dreams, and I will see you in the next one.